So, in the previous section, I talked about what goes wrong with many textbook models of measurement in quantum field theory. Although, really, I should hesitate to call them models because they basically wave their hands and don't provide a model. Um, so, we need to provide a model for our measurement devices. And there are two state of the art approaches to modeling measurements of quantum fields, which need discussion here. There's the Fewster Verch framework, in which one quantum field acts as a localized probe on another quantum field, and that whole process is formalized within the framework of algebraic QFT. And on the other hand, there's the Unruh DeWitt detector, in which a non-relativistic atom-like probe is coupled to the quantum field. And we can compare these two models of measurement on two sets of criteria. I want to ask, how well does each model preserve the central commandments of relativity, covariance, causality, and locality? And how well does each model connect with experimental practice? And for a technical comparison, you can see this paper referenced down here. So let's start with the Fewster Verch framework. In the Fewster Verch framework, one quantum field acts as a probe on another. It's a very general framework, so we can't say much about it in general, but for one example here, which is discussed in this paper by Rupp, we take one massive Klein-Gordon field psi to be a probe of another massive Klein-Gordon field phi here with a joint Lagrangian, which looks like this. So we have the probe, the field being probed here, it's Lagrangian, and we have the field probing here, this Lagrangian. And then, for instance, just as an example, they might interact like this. Lambda is some coupling constant, which tells you how strongly the two systems interact with each other. And rho is an interaction profile, right? So it's a space-time function, rho of t and x, which is 0 outside of some region Ka. So it's compactly supported in some region Ka. So we have these two fields which exist side by side throughout the eternity of the universe, and they only interact with each other on this small little region here. So it's a localized interaction between these two fields, right? And then, at least in this Rupp paper, we then describe a processing region, NA, which is somewhere in the future of Ka, where the probe is processed and measured or analyzed, or somehow the information is pulled out of the probing field then. Right. So, that's just quickly what the Fewster Verch framework is like. How well does the Fewster Verch framework preserve the causality and covariance of our theory? The answer here is it does so absolutely perfectly. The Fewster Verch framework is formulated entirely within algebraic quantum field theory, and so all of this is guaranteed. It's really a mathematically very precise and description of what might be going on here, right? So the next question then is, how well does the Fewster Verch framework connect with experimental practice? The answer here, in principle, well, but practically barely at all. In principle, the Fewster Verch framework can handle anything that algebraic quantum field theory can handle. As I've mentioned, the Fewster Verch thing is a framework. You can input any sort of quantum field theory you'd like into it, and it tells you how that might interact with another one. And it's all very abstract and uncommitted within algebraic quantum field theory, or all described within algebraic quantum field theory, but the specifics are something you have to plug in, right? So it's a framework for building models. So it can, in principle, it can do anything a QFT can. But in practice, algebraic quantum field theory, and any quantum field theory really, can't handle much in terms of relating to actual experimental practice. And in particular, we don't have a way of describing interacting bound states like the hydrogen atom well in algebraic quantum field theory. The hydrogen atom is, suppose we have the electromagnetic field and an electron field and a proton field. I mean, pretend that there is such a thing as a proton field. Then describing these three, there should be something like a bound state solution to this. There should be some energy state of the theory which corresponds with the hydrogen atom, right? Some localized bound excited state of the quantum field theory where we have this description of the hydrogen atom. So that would be a second quantized description of the hydrogen atom. And we really don't have one of those, and you can't write down what that theory looks like in a QFT. Not because it's not possible, just because we don't currently know how to do that. And moreover, there's another issue with connecting with experimental practice, is that the Fewster Verch framework, it uses one quantum field theory to measure another quantum field theory. And at the end of the day, we're still left wondering how to measure a quantum field theory, how to get the information out of this and relate this to our experiments. If we don't really leave QFT land. And that's what lets it stay so perfect in terms of covariance, causality, and locality. But if we never leave QFT land, then we're never going to connect with our experiments. Okay, the second detector model is the Unruh DeWitt detector. It's a non-relativistic atom-like probe which is coupled to the quantum field. And again, there's many ways to do this, but just to give you one example here is an Unruh DeWitt detector coupled to a massive Klein-Gordon field phi. This may have this joint Lagrangian here. Here's the Lagrangian for the field, right? Here then is the Lagrangian for the probe, and you can basically assume whatever sort of internal structure you want for your Unruh DeWitt detector. There's a coupling constant, and then there's a smearing function, a sort of interaction profile, which is, again, you can take it to be compactly supported in some region Ka. You can take this to be whatever you like, but let's consider something compactly supported. And then there's these two operators here. The field operator at t and x couples to the probe internal degree of freedom mu here, which depends on the proper time of the detector, because we're doing it in the interaction picture, right? So here's the probe's internal degree of freedom. And this could be a number operator or a spin operator or any sort of operator you can make sense of in your non-relativistic probe, right? So this is how that works. So again, I stress it's a non-relativistic system coupled into a quantum field theory. And one important thing to note here is that this interaction profile, we can take it to be point-like, if we like, in the following sense. We can have it be proportional to a delta function in position, which is only non-zero on some trajectory, gamma, that the particle follows, right? So it's a delta function defined over this trajectory that the atom may follow. And here's a switching function which controls when that atom couples and when it doesn't couple to the field. So you can have these sort of point-like detectors moving through space-time, coupling to the field. And that's a very well-posed thing you can do. So how well do Unruh DeWitt detectors connect with experimental practice? Very well, in fact. The Unruh DeWitt detectors are very close fit to the light-matter interaction in certain regimes, and in some ways it improves on the models used in quantum optics because it is relativistically much more sound. Right? You can see that in these papers down here. How well does the Unruh DeWitt detector preserve the central commandments of relativity, of covariance and causality and locality? The answer here is that it does so imperfectly, and there's some papers you can read here about this, but with very well understood and controllable issues. Right? For point-like detectors, there's essentially no problems with covariance and causality, except that there are some divergences which show up if you switch the detector on and off too quickly. Right? But for smeared detectors, there are these Sorkin-like signaling issues, and there are some issues with time ordering. But up to certain orders in perturbation theory, these things don't matter. And so there are some regimes where it's in any regime where it's reasonable to talk about first quantized atoms, these issues are manageable, right? So we do break covariance and causality and locality in some small ways, but those things are well understood and controllable and not really an issue when first quantized atoms are realistic. So it's not a fundamental description of what's going on here, but it's a manageable and well understood one. So recall that what we're trying to do is establish a better theory to experiment connection, right? To connect our theory with actual real experimental practice. I want to go to the lab and explain their experiment in a way which supports my theory, right? So on balance, it seems to me that the Unruh DeWitt detector is going to be better positioned to help us with this. But I think we should formalize our situation a bit to get a better idea of how this comparison works. And that's going to involve talking about measurement chains and cuts.